Hello and welcome to this video. In this video we're going to be going through the topic of superconductors. So superconductors are very useful materials. Now a regular conductor, we can change its resistance by changing the temperature. Okay, so we would say for a regular conductor, if we were to increase the temperature, it would increase its resistance. This much we can agree on. Okay. Then we would say that for like semiconductors, if we had a thermistor, for example, so this is for regular ohmic conductors. Then for a thermistor, we would say the opposite. We would say that if we increase the temperature, we're actually going to reduce the resistance. So in the case of a thermistor, in order to get the lowest resistance possible, we have to have the highest temperature. So highest temperature possible equals the lowest resistance possible. Okay, the highest temperature possible is known as Planck's temperature, but we don't even know if it's physically possible for even stars to reach Planck temperature. So this is not really going to be a good method of being able to reduce the resistance of resistors, because if we're trying to get up to the temperature that's close to the temperature of stars on Earth, we're probably going to do some bad things with that. Okay, so we're trying not to get that high of a temperature. So ohmic conductors mean we can do the opposite. If I were to decrease the temperature, then it would decrease the resistance. Okay, so my idea is to get the lowest possible resistance, I need the lowest possible temperature. And so what we could do is take a regular ohmic resistor and we could just decrease the temperature all the way to absolute zero, or the lowest possible temperature we have is minus 273 degrees Celsius, what we would call 0 Kelvin. As we get to that temperature, most regular ohmic conductors or ohmic resistors will actually just still have resistance at absolute zero, and that's because there are still ions present, so it's still going to have collisions as long as the electrons have enough energy to move near to them. And so we can't actually get a zero resistance, or so it would seem, until we get a superconducting material. So superconducting materials are very special materials. So what a superconductor is it is a material. So it is a material which at or below what we would call its critical temperature its electrical resistance, and therefore it's also its resistivity, its electrical resistance falls to zero. Okay, so this means that for a superconductor, it is possible to get literally zero resistance, so zero collisions between electrons and the ions, which is quite phenomenal and which has very profound uses. So if we have something that has absolutely zero resistance, our uses for them can get quite profound. For example, the whole way we're currently transporting electricity around the UK is by the national grid, okay, which is the field lines that you see, or the lines, power lines that are above all the fields along the countryside, and they basically have to use transformers to try and increase the voltage as much as possible so we don't lose that much energy. What we could do is we could basically just replace all of those wires in the national grid with superconductors, and if we could do that and keep them cooled to that temperature, we'd never have to use transformers, because we wouldn't actually have to reduce the resistance, because the resistance is already zero. And so the national grid is one where using superconductors is just going to reduce the energy loss. Now, this isn't the only property that superconductors have. We will find out in A2 magnetic fields that if we have an electromagnet, meaning it's something that if we can put electricity through, we've already said that if we ever have an electric field, we have to have a magnetic field. And this electric field in a superconductor is going to be incredibly strong, which means its magnetic field is also incredibly strong. So a secondary property of superconductors is they have very strong electromagnets. Okay, which means their magnetic fields are very, very strong. And you can see this in effects such as the Meissner effect. And this is where you get like you could probably Google the Meissner effect and see a cool little video. If you get just a small cylinder of a superconducting material and you cool it down, so you'll usually see it in some sort of like petri dish, and then have poured like liquid nitrogen in it to cool it down, and you put a metal cube on top, the metal cube will just float above it. Okay, and this is what's known as the Meissner effect. But if I were to tap that cube, it would wobble around a bit, and then it would rest back into its original place. Whereas we also have a second effect that's very similar that we call quantum locking. And quantum locking is where instead of it being able to wobble, if I touched it, the whole thing would just move and then get stuck in its new position. But it doesn't wobble anywhere, it just gets stuck in those fixed positions in this magnetic field. So that use, having very strong electromagnets, is actually used in maglev trains. So these are currently available. Mostly in Japan, you can find a lot of maglev trains. Essentially, the way they work is we'd have superconductors in the tracks. So all of these tracks will contain superconductors, and where the wheels would usually be completely pushing down on these tracks, if we have small electromagnets in them, or we have a superconductor, it means that where instead of them pushing fully down, we can have a force that's acting upwards the same way as this levitation does, and so it would be a much gentler touching on this. And this is basically there so that it reduces the friction between the wheels, and so this means that we get less energy loss. So this also reduces energy loss. Now there's other uses, so these tend to be the main ones that are going to come up in your exam, but I'm going to let you in on some other uses that we would use them for. We could also use them in the production of quantum computers, which has been all over the media recently with Google, IBM, companies like this, all releasing all of their record-breaking quantum computer stats. Quantum computers, because they are so powerful, have to have zero electrical resistance. This is also because they need to control all of those weird quantum effects like tunneling or entanglement or anything like that. So we need to basically, for a quantum computer to work efficiently, we need to make sure that we have exactly zero electrical resistance. And so this is another use that we can have for it. But all of these uses come with a cost. We can't ever have something this perfect. If something was this perfect, surely we'd have done this all already. We'd have had superconductors in the national grid. We have maglev trains going everywhere. Why don't we actually put this into effect? So now let's look at some of the problems surrounding superconductors currently. The main problem that we have is the temperature that they have to work at. So they only operate, or most of them will only operate at a few degrees above absolute zero. Okay, so a few Kelvin, I'm going to call it. Okay, so it's usually a very average critical temperature will be about 4 Kelvin, which is very, very, very cold. Okay, so this means that we're actually going to have to use up a lot of energy to reduce the temperatures to be about 4 Kelvin. So it takes a lot of energy to make the material a superconductor. So it has to meet that condition of being at or below its critical temperature, and so it takes a lot of energy to make the material superconducting. And what we actually find when we do the calculation is that the amount of energy that we're using to force these things to be superconductors is a lot more than the energy we're saving them from them being superconductors. So we use more energy than we save. And that's a problem, because if our whole uses of these, both in maglev and national grid, is we're trying to reduce the energy loss. But if we're using more energy to save a smaller amount of energy, then what's the point? Okay, so this is the biggest problem with superconductors, is the fact that they have to be just a few degrees above absolute zero. But there's also this idea that we have to maintain this temperature. So maintaining those conditions is also very hard, because as soon as it rises above the critical temperature, we lose that superconductibility. Okay, so we have to maintain the conditions. And what they don't go through in the A-level spec, but is very true, is it doesn't just have to be the temperature. We can also affect the pressure on a superconductor to be able to change its critical temperature. But again, making very high pressures means that we have to have very high costs, and the amount of energy that we're using to make these high pressures is going to be much greater than the energy that we save from actually putting these superconductors into use. So our solutions to this, so we do have supercomputers, we have quantum computers, and so we have got superconductors to work and behave in this, and we can maintain them. And the reason is because our general solution to this is we want high temperature. I'm going to put high temperature in quotations because they're not actually high temperature, but they are relative to what it should be. High temperature superconductors. Okay, this is our solution. We want to find a material that ideally is a superconductor at room temperature. The ones that we found so far for a while, yttrium barium cuprate was the highest temperature superconductor, yttrium barium cuprate, and you tend to find that most of these high temperature superconductors are a cuprate. Cuprate is the kind of brittle material that your dinner plates or that kind of stuff is made up of. It's not a very strong material. So that means that this, while it is very useful, is also very delicate. We have to kind of be careful with these things. And the main reason that this helps is because with going to 4 Kelvin, we usually have to cool things down to 4 Kelvin using liquid helium, which is not only very difficult to obtain, it's also very difficult to maintain. If you are unaware, liquid helium will actually act as a superfluid, so it's very hard to contain in a container, because if you put it into like a cup or a bowl, it will, because it is a superfluid, it has the ability to just crawl up the side of the bowl and then start spilling out, essentially defying, appearing to defy gravity. The easier thing with yttrium barium cuprate, and we've also found some hydrogen sulfides that are, I think, the current highest temperature that we have from a bunch of German physicists. These things can be cooled by liquid nitrogen, and liquid nitrogen is much easier to obtain, and so it means that if we can cool something down using liquid nitrogen, it means we have a better chance of actually maintaining these superconductors. Okay, so this is the extent that you have to know for A-levels. I'm going to do a little bit extra now that's going to try and explain briefly how these superconductors work for anyone that's interested. You won't have to know this for your A-level spec. I just feel like this is extra information to try and pique your interests, so you might go out and then hopefully increase your knowledge on superconductors. So how do superconductors work? How do superconductors work? Okay, this is a quite a high level concept to try and wrap your head around, but I'll try and simplify it down to make it easy. So superconductors work by a phenomenon that we call Cooper pairs. Okay, so Cooper pairs are just two electrons that have kind of forming what appears to be a bond between them, but we'll see what actually happens. The Cooper pairs, what's happening is as soon as we reach that critical temperature, all of these things are positive, and the electron, the first electron in this Cooper pair, is going to travel through this gap. Okay, as soon as it travels through this gap, because there was once an electron there, but now there isn't, the negative field basically gets taken out by this positive field. Okay, so this is a positive field, which means that as the electron travels through here and leaves, it's also going to have a positive field through here. And if this first electron keeps going and doesn't collide with anything, then we actually get the second electron is going to be attracted to the positive field. So it will go directly along the same path, and that is what the Cooper pair is. Okay, so this is a very simple version. There's obviously a lot more complicated ways of explaining it. This is probably the simplest version to explain it. And what this means is that if we have Cooper pairs and then we have all of the electrons all following the same paths, then none of them will ever collide, and then we get zero resistance. So hopefully this helps to make a little bit more sense of why this phenomenon of superconductors actually works. Hopefully all of this content does make sense, and hopefully you're as interested in it as I am, and thank you for watching.